configuration and motion of the Earth, the Sun and the other planets in the solar system was debated for ages till Ptolemy, a Greek scientist, put forward his geocentric theory. His theory stated that the Earth is at the center of the universe and that the planets, stars and the Sun revolve around the Earth in circular orbits. Later, Copernicus, a Polish monk, put forward his heliocentric theory, which stated that Sun is at the center of the solar system and that all the planets, including the Earth, revolve around it in circular orbits. And then Johannes Kepler, building on the work by Tycho Brahe, formulated the three famous laws of planetary motion that have been named after him. They are the law of orbits, the law of areas, and the law of periods. The first law, the law of orbits, states that all the planets revolve in elliptical orbits with the Sun at one of the foci of the ellipse. Let us conduct an activity to better understand this. Fix a drawing sheet to a pin board. Select 2 points, F1 and F2 on the board and fix 2 pins at the points. Take a string of finite length and pass it through a small ring. Fix the 2 free ends of the string to the 2 pins located at F1 and F2. Pass a thin pencil through the small ring. Stretch the string taut at the tip of the pencil and draw a curve on the sheet by moving the pencil as shown. Take care that the string is taut while you draw the curve. The closed curve you observe is the ellipse. Points F1 and F2 are called the foci. The midpoint of AB, which is denoted as O, is the center of the ellipse. For any point P on the ellipse, the sum of the lengths PF1 and PF2 is constant. So, as per the first law, the Sun is at one of the foci of the ellipse and the planets rotate around it in elliptical orbits. Also note that sum of the lengths PF1 and PF2 is always constant. Kepler's second law of planetary motion is the law of areas. According to this law, the line joining the Sun and a planet sweeps equal areas in equal intervals of time. Consider a planet revolving around the Sun. Let P1 and P2 represent its position at the start and end of a 30-day duration. Let A1 represent the area swept during this period. Similarly, let P3 and P4 represent 2 positions of the Earth during its revolution for a 30-day duration, represented by A2. According to Kepler's second law of planetary motion, area A1 equals area A2. The concept of Kepler's second law can be understood by the fact that the angular momentum of the planet revolving in its orbit remains constant. This is because it is under the influence of a central force. The force of attraction pulls the planet towards the Sun, and the magnitude depends on the distance between them. For a body under the action of a central force, the angular momentum L, which is the product of mvr, remains constant. Here, r is the radius vector, v is the velocity vector, and m the mass of the body. If p is the linear momentum of the body, then L is equal to r into p. If delta t is the time in which the radius vector sweeps an area, delta A, then delta A is equal to half multiplied by r multiplied by v delta t. Thus, delta A by delta t is equal to half r multiplied by v. On simplification, we get delta A by delta t is equal to half L by m. As L is constant, delta A by delta t is also constant. Hence, for a given time interval, delta t and delta A remain constant, thus proving Kepler's second law. Kepler's third law of planetary motion is called the law of periods. According to this law, the square of the time period of a planet is directly proportional to the cube of the semi-major axis of its elliptical orbit. That is, t squared is proportional to r cubed, where t is the time taken by the planet for one rotation and r is the length of the semi-major axis of its elliptical orbit. Kepler's laws revolutionized the field of astronomy and have helped people understand the configuration and movement of planets better. Most of us are aware of Newton's conclusion on an apple falling from a tree and the subsequent discovery of gravitational force. He showed that the force responsible for the fall of that apple was the same as the force that held the moon in its orbit. This implies that the force of attraction between any two bodies applies to all the bodies in the universe. This force is referred to as gravitational force. The word gravity is derived from Latin meaning heavy. The moon revolving around the Earth is under the action of centripetal force, which makes it follow a curved path. This centripetal force is provided by the gravitational force between the Earth and the moon, similar to that of the force between the moon and the Earth. The magnitude of the gravitational force between any two objects varies with the distance between them, as well as their masses. According to Newton, the moon revolving around the Earth has a centripetal force, which is due to the Earth's gravitational force. The centripetal acceleration of the Moon is given by the expression am equal to v square by rm, where v is the speed of the Moon in its orbit and rm is the distance between the Moon and the Earth. The velocity of the Moon in its orbit is derived from the fact that the Moon's orbit is circular of radius rm and its revolution period is t. Thus, the orbital velocity of Moon is equal to circumference of the orbit by its time period, which is equal to 2 pi rm divided by t. The expression on simplification gives us am equal to 4 pi square rm by t square. Substituting the values of rm and t in the expression and simplifying, the acceleration of the Moon obtained is much less than the acceleration of a freely falling body on the surface of the Earth. From this observation, Newton concluded that the magnitude of the Earth's gravitational force decreases with distance. Thus, based on the observations regarding forces, Newton proposed the Universal Law of Gravitation. It states that every particle in the universe attracts other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Thus, the law can be expressed as shown here. Combining the two expressions, we get F is directly proportional to m1 into m2 by r square. Here, m1 and m2 are point masses and r is the distance between the two particles. Replacing the proportionality sign with the equal to symbol, we get a constant g, called the universal gravitational constant. It is called the universal constant as its value 6.67 into 10 to the power minus 11 Newton meter square per kg square remains the same throughout the universe. Now, let's consider a coordinate system having position vectors r1 and r2. When we apply the law to 2 point masses m1 and m2 in the coordinate system, we get the mathematical expression for the gravitational force of m1 on m2 as F12 is equal to gm1 m2 by mod of r12 cube into minus r12, where r12 is the vector in the direction m1 to m2, which is equal to r2 minus r1. In the given expression, we use bold letters to represent the vectors. The negative sign indicates that the force is an attractive force and acts in the direction of minus r12, which is m2 to m1. Thus, the same expression can be written as F12 is equal to minus gm1 m2 by r12 square into r cap, where r cap is the unit vector in the direction m1 to m2. In this expression, the quantity gm1 m2 by r12 square is the magnitude of the force and can be denoted as modulus of F12. If F21 represents the gravitational force on point mass m1 due to point mass m2, then F12 represents the gravitational force on m2 due to m1. According to Newton's third law of motion, both the forces F12 and F21 are equal in magnitude and opposite in direction. Now, let's consider a system with more than 2 point masses, say M1, M2, M3, M4 and M5, placed at different positions in space. In this case, the net gravitational pull forces exerted on a single mass, say M1, is the vector sum of the gravitational pull forces of all the other 4 masses on M1. Thus, the net gravitational force on the particle of mass M1 is given by F1 net is equal to the vector sum of F21, F31, F41 and F51. Now let's try to find the gravitational forces between extended objects, which are huge in size, like the Earth and the Moon. For this, we need to find the vector sum of the gravitational forces of all the particles that constitute the body. This can be obtained by using calculus. When we deal with the gravitational forces between extended bodies, we need to consider 2 special cases. The first one is the gravitational force of attraction between a hollow spherical shell of uniform mass, density, and a point mass resting outside the surface is equal to the gravitational force between the point mass and the mass of the shell concentrated at its center. The second one is, if we consider a point mass within a hollow spherical shell of uniform density, the force of attraction due to the shell on a point mass situated inside it is 0. Let us learn about these cases in detail. The hollow shell can be considered to be consisting of several point masses along its surface. For example, consider the circular strip of the shell and the point masses on it. Gravitational forces caused by various point masses on the circular strip of the shell have 2 components of the forces, one along the line joining the point mass and the center of the shell, and the other perpendicular to it. The perpendicular components cancel each other, making the resultant force acting along the line joining the point mass and the center of the shell. The magnitude of this net force is equal to the force between the point mass outside the shell and the total mass of the shell concentrated at its center. Now let us look in detail about the second case. In this case, again consider different regions of the spherical shell that contain point masses. The point masses on different regions of the shell attract the point mass inside it in different directions. These forces cancel each other completely, and hence the resultant gravitational force on the point mass inside it is 0. Thus, the gravitational force between extended objects differs from one situation to another. We learned earlier about the gravitational force between 2 bodies of masses m1 and m2 separated by a distance r. The expression for the force is given as F is equal to G into m1 multiplied by m2 by r square. where G is the universal gravitational constant. In the expression, G is referred to as universal constant, as its value is constant in any place in the universe. The value of G was experimentally found by Henry Cavendish during his effort to find the density of the Earth. Have a look at Cavendish's apparatus. It consists of two pairs of spheres. One, a small pair of spheres, and the next is a large pair of metallic spheres. Now let us try to understand how this instrument helps measure the universal gravitational constant, G. Basically, the smaller pair of spheres is attached to either side of a light wooden rod, suspended from a rigid support by quartz fiber, and is free to rotate by twisting the fiber. The setup is kept within a closed environment to avoid air currents. The other two larger metallic spheres are brought from a distance close to the smaller spheres. They are placed at an equal distance on either side of the small spheres so that all the four spheres lie in concentric circles. The gravitational force of attraction between the smaller and the bigger spheres causes the smaller ones to move towards the larger ones. Hence, they move along the arc of a circle with a radius equal to half the length of the rod. The system of horizontal rods rotates till the torque due to gravitational force between the spheres equals the restoring torque on them. Thus, we have equation 1. The negative sign in this equation indicates that both the torques act in opposite directions. The total torque due to gravitational force between the spheres is denoted by equation 2. Here, r is the distance between the centers of the spheres and L is the length of the rod. The restoring torque is denoted by equation 3. Here, K is the restoring couple per unit angle, and theta is the angle through which the system of smaller spheres twist. The value of K can be derived by applying a known torque and measuring the corresponding angle. We equate equations 2 and 3 and hence deduce the expression for G. The value of theta can be obtained precisely by using the lamp, mirror, and the scale arrangement as shown here. By knowing the values of the other quantities in the expression, the accurate value of G is found to be 6.67259 multiplied by 10 raised to the power minus 11 Newton meter square per kg square. Interestingly, this is how Cavendish attempted to measure the mass of the Earth and subsequently its density. Assume the gravitational force of attraction between Earth and a small sphere of mass m on its surface is denoted by equation 4. It is the same force that is referred to as the weight of the body W, given by mg, where g is the acceleration due to gravity on the surface of the Earth. Equating equations 4 and 5, we get the expression for acceleration due to gravity in terms of g, radius of the Earth, and its mass. To determine the value of g, we can perform simple activities like dropping a body from a known height and measuring the time taken to descend. Knowing the values of the radius of the Earth and the knowledge of the value of g enables one to measure the mass of the Earth. In your earlier session, you learned about acceleration due to gravity on the surface of the Earth. The expression for acceleration due to gravity on the surface of the Earth is given by equation 1 as the product of universal gravitational constant g and mass of the Earth me divided by square of the radius of the Earth re. This is basically derived from the gravitational force between the Earth and a body on its surface, which is indicated by equation 2. F equals gme into m divided by re square, where m is the mass of the body on the surface of the Earth. Now let us assume that the body, that is the sphere, is taken away from the surface of the Earth to a height h, which is comparable to the radius of the Earth. The body placed at a given height experiences the gravitational force due to the Earth. It is represented in equation 3. F equals gme into m divided by square of re plus h. This gravitational force on the body towards the Earth is its weight. Since the weight of the body is determined by the product of its mass and acceleration due to gravity at a given height, the weight of the body at a given height is expressed as in equation 4. Fh equal to Wh, which is equal to m into Gh. In this equation, Gh is acceleration due to gravity at a given height from the surface of the Earth. We can obtain acceleration due to gravity at a given height by equating 3 and 4. Let this expression be equation 5. Comparing equations 1 and 5, we get the ratio of acceleration due to gravity at a given height to that on the surface of the Earth. Simplifying the expression, we get acceleration due to gravity at a given height as in equation 6. Gh is equal to g into 1 plus h by re power minus 2. If the height of the body is much less than the radius of the Earth, then the ratio of h to re is much less than 1. Then, using the binomial expansion of the term in the parentheses, we arrive at the expression as equation 7. Gh equal to g into 1 minus 2 h by re. To consider the variation of acceleration due to gravity below the surface of the Earth, let us assume that the Earth is a perfect sphere of uniform mass density ρ. Based on the formula, mass is equal to volume into density. The mass of the Earth is represented by equation 8. Me equals to 4 by 3 pi re cube into ρ. Hence, equation 9, which indicates acceleration due to gravity on the surface of the Earth, can be modified to as equation 10. G is equal to 4 by 3 G pi Re into rho. Now, consider a point mass placed at depth d below the surface of the Earth. The Earth is considered to be made of a concentric shell of thickness d and a sphere of mass ms and radius re minus d as indicated. Thus, the mass of the inner sphere of Earth is represented by equation 11. Ms is equal to 4 by 3 pi into cube of Re minus d into rho. Here, gravitational force between the shell and the point mass is 0, as it lies inside the shell. However, there exists a gravitational force between the point mass and the part of the Earth of mass ms, as the point mass lies outside it. Thus, acceleration due to gravity on the surface of the sphere of radius Re minus d can be written as equation 12. Gd is equal to G divided by square of Re minus d multiplied with ms. This gives acceleration due to gravity at depth d, indicated by equation 13. Gd is equal to 4 by 3 G pi into Re minus d multiplied with rho. Acceleration due to gravity at depth d inside the Earth can be compared with that on the surface by considering the ratio shown using equations 10 and 13. On simplification, we get equation 14, which indicates acceleration due to gravity at a given depth from the surface of the Earth as Gd is equal to G multiplied by 1 minus of d by Re. That's how we derive the expression for measuring G above and below the Earth's surface. Earlier, you learned that when a body is lifted to a height from the surface of the Earth, the work done on the body is denoted by the expression W is equal to mgh, where m is the mass of the body. When a body is at ground level, the work done on the body is 0, as its height is 0. Thus, the ground is taken as the reference level or the datum level. The work done on the body while lifting is stored in it in the form of gravitational potential energy. If the position of a body is changed by the application of a force, the change in the potential energy of the body is equal to the amount of work done on the body. Now consider a body moved vertically from a point at a height h1 to another point at a height h2 as shown. The difference in the gravitational potential energy at these 2 points is equal to the work done by the force applied on it while lifting it through the height between the 2 points. The concept of change in gravitational potential energy of a body is calculated by the product of its mass, acceleration due to gravity at the given place, and the change in the height of the body from the chosen reference level. This is not applicable when we consider a point very far from the surface of the Earth, as the value of acceleration due to gravity is no more constant. Thus, the expression mg as the force acting on the body due to gravitational pull of the Earth is not applicable at that distance. To understand the concept of change in gravitational potential energy of a two-particle system, we use the gravitational force between the two and the concept of integral calculus. Now, consider a particle of mass m1 placed at a fixed position A and another of mass m2 moved from position B to C as shown. In moving the second particle from B to C, consider an arbitrary position D, where its distance from A at a given moment is r. The gravitational force of attraction between particles of masses m1 and m2, separated by distance r, which acts along dA, is g into m1 m2 divided by r square. Let this be equation 1. If the particle is moved through an infinitesimally small distance, dr, as shown, the work done by the gravitational force on the second particle is denoted by minus f dr. On substituting f in this expression, you get minus g into m1 m2 divided by r square into dr. Let this be equation 2. The negative sign in the equation is due to the fact that the direction of the displacement is opposite to that of the force. By definition, the negative work done on the second particle is equal to the change in gravitational potential energy of the two-particle system during this small displacement. Thus, Fdr is equal to g into m1 m2 divided by r square into dr. Let this expression be equation 3. The change in gravitational potential energy of the two-particle system as the second particle moves from B to C is a function of the distance r, is denoted by ur2 minus ur1 is equal to the integral of du within the limits r1 to r2. This is equal to the integral of gm1 m2 by r square dr within the limit r1 to r2. Let this be equation 4. On simplification, we get the expression ur2 minus ur1 is equal to gm1 m2 into 1 by r1 minus 1 by r2. Let this expression be equation 5. Now consider the distance between the two particles is infinity. In this case, the potential energy of the system is chosen to be 0. Thus, U infinity is equal to 0. In general, while defining the gravitational potential energy of a two-particle system, we bring a particle from infinity close to another particle. In this expression, R1 is infinity and R2 is equal to R. By applying this to the two-particle system considered, we bring the second particle from infinity close to the first particle. Here, UR is equal to UR2 minus UR1, which is equal to UR minus U infinity. As U infinity is 0, the same expression can be written as UR is equal to UR minus 0. Thus, the gravitational potential energy of the two-particle system separated by distance r is denoted by UR is equal to minus of gm1 into m2 by r. Let this be equation 6. In this system, if the mass of one particle, say m1, is taken to be unity and the mass of m2 as m, then the energy of the two-particle system is UR is equal to minus gm divided by r. This is defined as the gravitational potential at a distance r from particle of mass m, measured in joule per kilogram. So far we have considered a two-particle system. If we consider a three-particle system, say at positions P, Q and R as shown, we have three pairs of particles, PQ, PR and QR. Thus, the total gravitational potential energy of the three-particle system is the sum of the potential for the three pairs of particles. Extrapolating this application of superposition principle to an isolated system containing n number of particles, the total potential energy of the system of particles is equal to the sum of the energies of all the possible pairs of its constituent particles. Thus, you have learned about the gravitational potential energy in two-particle and three-particle systems. If you throw a body vertically upwards with some velocity from the ground, it attains the height where its velocity becomes zero and then returns to the point of projection. As soon as the body is thrown, it is under G acting towards the center of the Earth. When the body is on its way up, it is under retardation till it attains zero velocity and then returns to the ground due to gravitational pull. Here, as the body moves up, its kinetic energy is converted into potential energy. This is based on the law of conservation of energy, that the total energy of the system remains constant. Thus, it is obvious that if the velocity of projection is increased, the maximum height attained by the body increases. But whatever the maximum height attained by the body projected vertically upwards, you feel that the body comes back to the Earth. Is it possible to project a body vertically upwards at such great speed that it does not return to the ground? Here's another way to ask the same question. Is it possible to project a body vertically upwards with a speed that allows it to escape the gravitational field of the Earth? If it is possible, the speed will be the escape speed of the object. Sometimes, escape speed is also referred to as escape velocity. For the time being, assume this is possible. In this case, does the escape speed of different objects depend on their masses? Let's answer the question with the same example. consider a position A on the surface of the Earth, from where the body of mass m is projected vertically upwards with velocity u. Then, its kinetic energy at the surface of the Earth is given by half mu square. Let this be equation 1. The potential energy of the Earth body system at the Earth's surface is denoted by PEA is equal to minus GMEM divided by RE. Let this be equation 2. In this equation, ME is the mass of the Earth and RE is the radius of the Earth. Thus, the total energy of the body on the surface of the Earth when it is projected vertically upwards is the sum of its kinetic and potential energies, and is denoted by the expression TEA is equal to half mu square minus GMEM divided by RE. Let this be equation 3. Now, assume the body moves continuously in the upward direction with a continuous change in its velocity. At position B, the height gained by the body is h, and its velocity at this position is v. Then the kinetic energy of the body at the height gained is expressed as half mv square. Let this be equation 4. The potential energy of the Earth body system when the body is at height h is denoted by the equation PEP is equal to minus GMEM divided by RE plus h. Let this be equation 5. Thus, the total energy of the body at position B is expressed as the sum of equations 4 and 5. Let this expression be equation 6. According to the law of conservation of energy, the total energy of the Earth body system at position B is equal to the total energy at position A, denoted by equation 7. On submitting the corresponding terms for the respective energies in equation 7, and on further simplification, you get the equation for kinetic energy of the body at the given height, as expressed in equation 8. The height gained by the body projected vertically upwards is maximum when its velocity v becomes 0. This is possible when the sum of all the terms on the right side of equation 8 is equal to 0. In case velocity v always has a positive value, then the body continues to move vertically upwards, thus increasing the value of h to infinity, which eventually happens when the body escapes the gravitational field of the Earth. This is possible when the combination of the terms in the right side of equation 8 is greater than or equal to 0 for any value of height h. Thus, the minimum value of u can be obtained by equating the expression to 0. Also, when h becomes infinity, the expression that includes h in equation 8 becomes 0. Rearranging the terms in the equation and simplifying, you get the value of U as given by the equation U is equal to square root of 2 GME divided by RE. Let this be equation 9. If this was the minimum value of velocity of projection of a body vertically upwards, then the body would escape the Earth's gravitational field. Thus, equation 9 represents the expression for the escape speed of a body on the surface of the Earth. It is clear from the expression that the value of the escape speed of a body on a given planet does not depend on the mass of the body. It depends on the mass of the planet and the radius of the planet. If the body is projected from a height h from the surface of the Earth, then the escape speed from that height is obtained by replacing the denominator of equation 9 with Re plus h as shown in equation 10. Using the relation of acceleration due to gravity on the surface of the Earth and the mass, radius of the Earth and universal gravitational constant, and simplifying, you get equation 11. Satellites are celestial objects that revolve around planets. As planets themselves revolve around the Sun, they too are considered satellites. Thus, Kepler's laws of motion are applicable to satellites too. The Earth's natural satellite is the Moon. The orbit of the Moon is nearly circular. Hence, the Moon is under the action of a centripetal force. This centripetal force is provided by the gravitational force between the Earth and the Moon. Now, consider the height of the Moon from the surface of the Earth as h and Re as the radius of the Earth. Then, the effective radius of the Moon's orbit is Re plus h. The centripetal force on the Moon is expressed as Fc is equal to mv square by Re plus h, where m is the mass of the Moon and v is the speed of the Moon in its orbit. The speed of the Moon in its orbit is also referred to as orbital speed. Let this expression be equation 1. The gravitational force between the Moon and the Earth is expressed as Fg is equal to gmem by Re plus h square, where me is the mass of the Earth. Let this be equation 2. Equating the two equations and simplifying, you get the expression for the speed of the Moon in its orbit as square root of gme divided by Re plus h. Let this be equation 3. Once you know the expression for the speed of Moon in its orbit, you can find the kinetic energy of the Moon using the expression Ke is equal to half mv square. Substituting the expression for speed from equation 3 in the expression for kinetic energy, you get the expression for kinetic energy as Ke is equal to half m gme divided by Re plus h. Let this be equation 4. Earlier, you learnt about the potential energy of a two-body system. Applying the concept of potential energy to the Earth-Moon system, you get the expression for potential energy as Pe is equal to minus gmem divided by RE plus H. Let this be equation 5. Now the total energy of the Moon in its orbit is determined by the sum of its kinetic energy and potential energy. Thus, the total energy of the Moon or any given satellite revolving in its orbit around the Earth at a given height is expressed as minus of GMEM divided by 2 times RE plus H. The total energy of an orbiting satellite is found to be negative. Let this be equation 6. Now, let's see what happens if the orbit of a given satellite is close to the surface of the Earth. In this case, the height h of the satellite becomes negligible when compared to the radius of the Earth. Thus, h in equation 6 can be neglected, and you get the expression for total energy of an orbiting satellite as TE is equal to minus GMEM divided by 2RE. Let this be equation 7. The speed of the satellite in its orbit is obtained by substituting 0 for h in equation 3. This gives the speed of the satellite in its orbit as v equal to square root of GME by RE. Let this be equation 8. Using the relation between acceleration due to gravity on the surface of the Earth and the universal gravitational constant, the orbital speed of the satellite can be expressed as v equals square root of GRE. Let this be equation 9. The speed of the orbiting satellite can also be obtained using the relation between the time taken by the orbiting satellite in its orbit, t, also known as the period of the satellite, and the length of the orbit. As the orbit is circular, the length of the orbit is the circumference of the circle, 2 pi RE. Thus, the speed of the satellite in its orbit is given by the expression v is equal to 2 pi RE divided by t. On rearranging the expression, you get the time period as t is equal to 2 pi RE divided by v. Substituting the expression for v from equation 8. In this expression, and simplifying, you get the square of the time period proportional to the cube of the radius of the orbit. This expression shows that it is in compliance with Kepler's third law. In today's world, communication plays an important role. Satellites are used for effective communication. Apart from communication, satellites are used for various purposes ranging from analysis of weather conditions in a region, live transmission of cricket matches through television, exploration of minerals from the Earth, and for geographical purposes. Satellites used for various purposes are artificial satellites. In a broader sense, there are two categories of artificial satellites, namely geosynchronous and sun-synchronous satellites. First, you will learn about geosynchronous satellites. Earlier, you learned that the speed of an Earth satellite in its orbit is denoted by the expression v is equal to 2 pi into re plus h divided by t, where re is the radius of the Earth, h is the height of the satellite from the Earth's surface, and t is the time taken by the satellite to complete one revolution around the Earth, which is referred to as its time period. Let this be equation 1. The speed of a satellite in its orbit can also be obtained using the relation v is equal to the square root of gme divided by re plus h, where me is the mass of the Earth and g is the universal gravitational constant. Let this be equation 2. Equating expressions 1 and 2 and simplifying, you get the expression for h, as shown in equation 3. Knowing the data for the mass of the Earth, its radius and universal gravitational constant, you can estimate the height of the satellite for which the period of revolution is 24 hours. This is done by substituting the corresponding values in equation 3 and simplifying as shown. Thus, a satellite whose height from the surface of the Earth is about 35,850 kilometers has a period of revolution equal to that of the period of rotation of the Earth. If the orbit of the satellite is in the equatorial plane of the Earth, then the satellite appears to be stationary relative to a position on the surface of the Earth. Such satellites are called geostationary satellites or geosynchronous satellites, as their motion in their orbit is synchronized with the rotation of the Earth. Generally, this type of satellite is used for telecommunications and mass communications. The International Satellite System, generally referred to as INSAT, is a series of geostationary satellites set up by Indian Space Research Organisation (ISRO) to cater the meteorological, telecommunications and broadcasting needs of the country. Now, you will learn about the second type of artificial satellite, a sun-synchronous satellite, also referred to as a polar satellite. The altitude of a polar satellite is lower than that of a geostationary satellite. that is, in the range of 700 to 1700 kilometers. Accordingly, the time period of such a satellite is of the order of a few hours. The orbit of these satellites is such that the satellite moves in a plane that is near normal to the equatorial plane, moving closely to the poles of the Earth for every revolution, while the Earth rotates in west to east direction. Why are these planets called sun-synchronous? As you know, the local time at a given place on the Earth depends on the longitude of the place. With the rotation of the Earth, the local time at a given place changes with the relative position of the Sun. The orbit of a sun-synchronous satellite is designed in such a way that the angle between the plane of the orbit and the line joining the Earth and the Sun are fixed. This maintains consistency in the lightning conditions of a given place. When a satellite revolves around the Earth, successive north-south passes are displaced the same distance as the Earth rotates during one orbital period of the satellite. As a result, the satellite covers the given place at the same local sun time daily. Thus, the motion of the satellite is synchronized with the local sun time at the given place. Hence, these types of satellites are called sun-synchronous satellites. As they cover the polar regions for every revolution, these satellites are referred to as polar satellites. As the altitude of a polar satellite is less, a camera fixed to the satellite can scan only a small strip of the Earth in one revolution. For the next revolution, as the Earth rotates on its axis, the adjacent strip of the Earth is scanned. Thus, in a single day, the whole of the Earth is scanned in a series of strips. Indian remote sensing satellites, generally referred to as IRS, which are used for remote sensing applications, environmental studies, weather analysis, forecasting, and similar applications are examples of polar satellites. Artificial satellites are generally unmanned. At times, cosmonauts are sent along with satellites into space to conduct certain studies. In space, they feel zero gravity or weightlessness. The weight of a body is the force experienced by the body due to the gravitational pull of the Earth. A spring balance that measures the weight of a body works on the principle of extension of the spring. Under the action of the weight of the body attached to the balance, which is fixed to a rigid support. While measuring the weight of the body attached to the balance, the body is pulled downwards due to the Earth's gravity. It, in turn, exerts the same force on the spring downwards, causing its extension. This is indicated in the reading of the balance. If the balance is not suspended to the rigid support and is allowed to fall freely, then both the body and the spring balance fall down, with acceleration due to gravity. In this case, the force exerted on the body by the balance is 0. Hence, the stretching of the spring is 0. Thus, the spring balance reads 0 weight of the body. This situation is the weightlessness of the body. Thus, we can say that a body experiences 0 gravity or weightlessness in a free fall. In the case of a satellite orbiting the Earth, it is similar to any other freely falling body. But it has very high velocity in the tangential direction of its orbit, due to which it misses the Earth as it falls. Thus, every part of the satellite is in a state of free fall, and it is subjected to acceleration due to gravity in that position. Hence, cosmonauts in manned satellites experience weightlessness.